Let's go back to what we did last time. So what we wanted to prove, okay, so said G beta was the limit when n goes to infinity of 1 over n log Zn. Okay, well, provided this limit exists. Okay, and what we showed, we wanted to show, okay, that G beta is equal to, well, log D plus lambda beta if beta is smaller than beta c, and beta lambda prime beta c if beta is larger than beta c. Okay, and what we proved so far is that if beta is smaller than beta c, then the limit when n goes to infinity of 1 over n log Wn is equal to 0. Okay, because we proved that Wn converges to W infinity, which is positive. Okay, so this thing in particular, well, it's equivalent to this. Okay, because Wn is Zn divided by the expectation of Zn. And the expectation of Zn is just d to the power n exponential n on the beta. Okay, the other thing we showed was that if beta is larger than beta c, then for p equal to beta c over beta, we have that E Zn to the power p is smaller than exponential p beta lambda is equal. Okay, so no, it's smaller. Okay, this is what we proved. Okay, by our subadditivity argument. Okay, so from this, okay, we get that the probability that Znp, say Zn, say, is larger than okay, let's say n to some power, perhaps n to the power 2 over p. Exponential beta lambda prime beta c. Well, this is smaller, okay, than n to the minus 2. Exponential p beta lambda prime beta c, which is smaller than n to the minus 2. Okay, so therefore, by Borel-Cantelli, we get that lim sup 1 over n is smaller than beta lambda prime beta c. Okay? And finally, so the last thing we have to prove is something about lim inf of 1 over n log Zn for beta larger than beta c. Okay, so this thing, okay, let's call it g bar of beta. Okay, and what we know is that well, this thing here, it's convex. Okay, it's the usual Hölder argument. Okay, you know you have a sum. So. Just Hölder, you know. Okay, so this makes log z convex, so 1 over log. So this is the limit fit of convex function. It's convex. So we know that g bar beta is equal to log d plus lambda beta if beta is smaller than beta c. So by convexity, okay, we have automatically that g bar beta, okay, it's larger than, well, I will just take the derivative of this at beta c. So the derivative of this at beta c, so I will get larger than beta minus beta c. The derivative of this as beta c, it's lambda prime beta c. And then I get minus log d minus lambda beta c. Okay, and by definition of beta c, I would say that this, and this cancel. And you get what you want. Okay, so this finishes the proof of the theorem we started last time. Yes, it's plus log plus lambda. Yes. Okay, so what's next? Okay, so rather than defining a new model, I want to give you a different perspective on this. And okay, as in the exercise list, you will have to prove perhaps a generalization of this statement. So what you can say is that basically what you're looking at, okay, is a population which is reproducing and walking at the same time. Okay, so like you start from one individual, okay. This individual will have two child, and to these two child you will associate location. Okay, so this is 0, and this is like okay, this is x empty set. This is x1. This is x2. Okay, and each of these two childs, they will have two children. And each of them will have a displacement. Okay, so this will be x11, x12, x, okay, x21, x22. Okay, and the question you may ask is, okay, you have Tn, which is the nth generation, okay, and you might ask, what is the height of the topmost children? Okay, what's the largest displacement I observe in my population? Okay, so first observation, we have solved this problem. Okay, this xv here, it's exactly the same as the h we had before, and we just say that well, h max n. Okay, and we have seen that h max n is equivalent when n goes to infinity to lambda prime beta c times n. Okay. Yeah. Basically, what I want to emphasize here is that somehow. In our proof, we didn't use all the assumptions we had, and here you can twist the model a little bit and keep the conclusion. Okay, so what you can do first is you can make the number of children random. Okay, and secondly, you can make the displacement of each child dependent on each other and dependent on the number of children. Okay, so in that case, the question is how do you define this? And basically, the clue is, well, you find the right martingale to define, you prove this theorem, and you get your answer. Okay, so this, I think I will put that in the list. I still have to write that. What we are going to see today is something rather different, is how you can push things further and find a more precise asymptotic about this. Okay, and for the sake of making things a bit easier to compute, okay, I'm going to consider the case where so d is equal to 2, okay, just like in my and omega. So you know here you have xv, which is the sum from n equal 1 to v omega vn. Okay. These are my displacements at each step. Okay, and I want these things to be standard Gaussians. Okay, so in that case, okay, remember that what was the criterion here for lambda prime? What we had was that lambda prime beta c lambda prime beta c minus lambda beta is equal to log d. Okay, in our case, this gives us beta c is equal to square root of 2 log 2. Okay, lambda beta, well, this is equal to beta square over 2. This is beta square. Okay, so you have beta square over 2 equal log d. So, okay, so let's make things even simpler. So we want to study the max over V in Tn of xv. Okay, and what you have is that xv, if you take a fixed v, this is normal of variance n. Okay, just because it's the sum of n standard normals. Okay, so let's look rather at the max of yv, okay, where yv are normal, but are also IID. Okay, here I have dependent random variables, okay? I have Gaussians, I can in fact write their covariance, okay? If I take two elements of V's, okay, and if I look at the covariance of xv and xv prime, the covariance, it would just be, well, the generation at which the path between v and v prime split. Okay, because it's really the number of increments you have in common between xv and xv prime. Okay, so let's make the covariance 0, and let's ask ourselves this question: what's the behavior of this thing? Okay, and just to convince you that this, these two questions are not completely unrelated, well, let me quickly show you that yeah, you get this square root of 2 log 2 appearing when you look at the max of yv already. So at first order, these things are the same. Okay, so okay, so let's write the theorem. Let's write a blank theorem, and then we will, within the proof, try to make things more accurate. So, okay, so the theorem is that y max n minus square root 2 log 2 n, okay, minus some other stuff, and perhaps renormalized by some stuff, converges to something in distribution. Okay, and we are only interested in convergence in distribution. Okay, because here somehow it would be a bit weird to put a dependence between generations. Okay, so somehow. Okay, so yeah, so what the thing is that controlling the distribution of y max is significantly easier than controlling the distribution of x max. Well, simply because if you look at the probability that what y max n is, let's make it smaller than u, yes. Well, it's equal to, well, the product over V in Tn that y max, that y v is smaller than u. And these things, so this is by independence, and these things are IID. So it's just 1 minus the probability that y0 is larger than u. Okay, to the power n. Okay, so our goal here is to find un. Okay, and un will depend on some other parameter as well. You will see why. But we want to find un, which is such that the probability that y0 is larger than un multiplied by n converge when n goes to infinity to something. Okay, why? Because then this thing will converge to the corresponding exponential, and this means that we would have a convergence in distribution here. Okay. I mean, a convergence in distribution provided that we rearrange terms. Okay, so that's the question. How do you find un here? Okay, the advantage is that we have a very explicit expression for this thing. Okay, it's just, well, the integral, okay, from u over square root of n to infinity exponential minus, well, s square over 2 ds, 1 over square root of 2 pi. Okay, so I want this to behave like 1 over n, roughly. Okay, so, well, first thing we want to do is perhaps replace this by some better asymptotic equivalence, something which is simpler to handle. Okay, so let's write a lemma here. Okay. Is it clear where we are going and what we are trying to do? So, well, it's kind of clear that, well, because we want this to be of order 1 over n, we are interested in the regime where u is much larger than square root of n. Okay, and so what we are interested in is the asymptotic of this integral when r is large. Well, and this is asymptotically equivalent to okay, so you will all learn something. 1 over r exponential minus r square root 2. Okay, basically, at the cost of putting this, you can just take the integral. Okay, and the proof here, okay, the proof is easy, and if you want more, if you want the next correction in the asymptotic is not too difficult either. Okay, so the proof, I will prove upper and lower bounds here. So what you have is that the integral from r to infinity of exponential minus s squared over 2 dr, well, it's smaller than the integral from r to infinity of s over r exponential minus s squared over 2 dr. And this is exactly 1 over r exponential minus r squared over 2. Okay, I'm just multiplying by something which is larger than 1. And the good thing is that now this thing is integrable. Integrable. I know a primitive of that function, which is exactly this one. Okay, if you want things in the other direction, well, I can do exactly the same thing. Except that in that, okay, R. Except that in that case, okay, I will limit myself to this range. Okay, and in that case, I will just take S over R plus 1. Okay, on this range, this is smaller than 1, so this is good. This is ds, right? And then I'm good, right? This is equal to 1 over r plus 1 exponential minus r squared over 2 minus exponential minus r plus 1 squared over 2. Okay, this is equivalent to 1 over r, and this thing is completely negligible with respect to that. Okay, so what we want is thus to find un. Okay, we want to find un such that, well, 1 over square root of n exponential minus unt square. Okay, sorry. Okay, let's see what we have here. Yeah, this n here yeah, I'm sorry. This is not n. This is 2 to the power n. Okay, so I want 2 to the power n. Then I get, well, 1 over square root of pi. And then I get 1 over r, which is just square root of n over un exponential minus un square over 2 n. I want this thing to converge when n goes to infinity to something non-trivial. Okay, so well, the first important bit to attack is this one. Okay, so basically you want this to be you want this at first order, okay, to be equal to n times 2 log 2. Okay, you want this to be at first order, sorry, n times log 2, okay, just to beat that. So it means that you want un to be equivalent to square root of 2 log 2 n. Okay? So basically, from this, you can get very easily that at first order, your y max is of order of this order. Okay? The reason why I'm saying this is that now I know that this term here, okay, it will be of order 1 over square root of n. So I know what I want my second, it will be of order, sorry. It will be of order square root of n. What's happening here?
Un should be on the side of this.
Yeah, there is no square root here. That's the point. Well, right. There is no square root. Okay, so this thing is of order 1 over square root of n, so we know what kind of correction we want. Okay, so this is equal. Okay, and yeah, you know that alpha n, okay, let's try to expand this. So here we get exponential minus un square over 2n. Well, this is equal to exponential. And here you have, well, minus log 2 times n, okay, which is what you get from this term squared. Okay, and then you get, well, you get twice the cross terms. So you get square root of 2 log 2. The division by 2 doesn't appear here, and then you get alpha n, and okay, you have a minus here. Okay, so this is the second term, and then you get minus alpha n square over 2n. And okay, so now remember, this thing, we just want it to kind of cancel these terms, cancel the square root of n thing. So alpha n here will need to be of order log n. Okay, so this thing you can completely neglect it. Okay, so this is equivalent, okay, if alpha n, okay, is little o of square root of n, and this is going to be the case. Okay, so what we are going to take is, well, alpha n is equal to, well, I have a 1 over square root of n here. So I want to multiply by square root of n. So alpha n will be minus 1/2 square root of 2 log 2 log n. Okay, and yeah, perhaps I want to put this plus t over square root of 2 log 2. No, okay, let's just put plus t. Okay, and then what I get is that the probability that y0 is larger than u and t, it converges when n goes to infinity to, well, I get 1 over square root of 2 pi then here the square root of n is going to be cancelled by the second term, so I just need to care about the constant. And the constant, I guess, is square root of 2 log 2, right? So 1 over square root of 2 log 2. And then I get exponential minus t over square root of 2 log 2. Okay, and from this, okay, I just plug it into there, and I get that the probability that y and max is smaller than u. Okay, it converges, what then, u and t, sorry. It converges when n goes to infinity to exponential 1 over square root of 2 pi. Well, okay, let me simplify this. So 2 square root of pi log 2 exponential, okay, exponential minus t over square root of 2 log 2. Okay, so what does this give us? Well, it tells you that if you're considering this, then this converges in distribution when n goes to infinity to z, okay, where the probability is that z is smaller than t, it's exactly equal to, well, this. Exponential 1 over 2 square root of pi log 2 exponential minus t over square root of 2 log 2. Okay, and okay, if you forget about, there is a minus here. There is a minus here, and there was always a minus, because this has to be smaller than 1 in the first place, right? Okay, so if you just ignore these things, so like this thing is a dilation factor, okay, and this thing is a translation factor. Okay, you can put it in there and replace this by t minus t0 if you want, where t0 is z. So if you make an affine transformation, okay, what you get is really just this z is just alpha z0 plus beta, okay, here. Alpha, I guess, is alpha is 1 over square root. Let me see. Alpha is square root of 2 log 2, sorry. And beta is whatever. Beta is okay, it has to be related to the log of this thing. So it's log 2 square root of pi log 2. And it has to be see it has to be multiplied by the square root of log 2. Okay, but it's not really important. What I'm saying is that just that this distribution here, it has a name. It's called the standard Gumbel distribution. And in fact, when you take the maximum of so many IID random variables, there are not so many things that can appear. So you have a limited number of distributions that can appear, and Gumbel is somehow is one of them. Is what happens when your distribution has a rather light tail. Light tail. Okay. Basically, if you have much heavier tail, you will get heavier distributions. For instance, if you have power tail, basically, the max here will also have power tail. Okay, I mean, it's just like when you prove central limit theorems, you do not have so much things that can appear in the limit, okay, because the limit has to be infinitely divisible. Here, when you take the max, you don't have so much things that appear in the limit due to other structural constraints. Okay, so yes, okay, we have a result, and now perhaps one would like to know how informative is it about this. So, yeah, the first thing you have is that basically here you have positive correlations between your variables, and this will tend to make the maximum smaller. Okay, because basically, yeah, if something is small, other things are also likely to be small because of positive correlation. So the question is, yeah, does it show in the limit? And if it shows, what's the effect? Okay, so I will try to prove something to you, and then, okay, we are going to try to prove an upper bound on this, which is like strictly better than this one. Okay, and then I will tell you what's the state of the art. So let me start with a basic and somehow, well, not impressive at all. Okay, it's not okay. So the proof is not that basic, but the result will not impress you given the one we have here. So what I want to show is that the probability that there exists n in 1n, okay, such that x, okay, and v in Tn, such that x Vn is larger than square root of 2 log 2 and plus, say, okay, I don't know the constant I have to put here. So, okay, let's put alpha log n here. And the probability that this happens, okay, perhaps I know the constant you have to put here. Let's see. I would say that this should be the right thing. Okay, so the probability that this happened is smaller than n to the minus 2. Okay, n to the minus 2 is just I want things to be. Sorry, I don't really care. Okay, I don't really care. So. Okay. So I want to show that basically the probability is that for some generation before generation n, I go much above this. Okay, is small. The important thing is that I want this to be simultaneously true for all generation before generation. Okay, and okay, the appeal here is that well, there is something here which is playing a role. So the probability is that this happened. Okay. Well, it's smaller than something. Okay. Well, it's smaller than the probability that Wn beta c is larger than, and I think this is what you get here. So let me check. Okay, so, okay, sorry. There exists n in 1n that Wn beta c is larger than exponential minus beta c log n. Okay, so this is true simply because when this happened, okay, what you have is that, well, you take the n in question here, okay, and what you have is that Wn beta c, it's larger than, well, okay, 1 over d, 1 over 2 to the n, okay, then you have exponential beta c square, because this is beta c, n, okay, minus lambda beta c, okay, so minus beta c square over 2 n, okay, and okay, and here you have this plus beta c, okay, plus beta c log n. Okay, and all these things they cancel out. Okay. Okay. Whoa. Okay. Beta c is equal to square root of 2 log 2. Okay. This is what you get from, you know, this beta times xvn. Okay. So you get 1 beta c squared. You get this beta c squared over 2, which is subtracted because this is lambda beta. Okay, so you get beta c squared over 2 times n. This is just log 2 times n, so this will cancel this thing, and you will just get the rest, okay, which is the overshoot of this level. Okay, and yeah, now you use basically the optional stopping theorem for martingale. The probability that a martingale that has average 1 goes above a certain level at some point is smaller than exponential beta c. Okay, so here what you put here is not important. You just need to put something that goes to infinity. Okay, and so now let me define the event A. Okay, let me call it AV. Okay, for V in Tn. AV will be the event. There exists an n in 1 n. Okay, that such that xvn is larger than square root. Plus square root of log n. Okay, and what I'm going to look at is, well, the probability that for all v in Tn, xv is smaller than u and t, and AV holds. Okay, and because of the lemma, okay, this is equal to the probability that for all v in Tn, xv smaller than u and t, plus a little O of 1 correction. Okay, because whatever you're missing here, well, it's contained in the union of AV complements, okay, and the union of AV complements, it has small probability. Okay, so the idea is that we are doing something a bit different. Okay, what we could do is we could just intersect this with the complement of this event. We are not doing that. We are doing something a bit more subtle. This is just to keep independence, okay? Well, not to keep independence, but basically to have a condition here that depends just on V, okay? When you, okay, and now we want to estimate this, okay? And we don't have independence, so we're not going to be able to factorize. But if we just want an upper bound, okay, we won't lose very much by doing a union bound. Okay, so 1. Now what I'm saying is that 1, it's smaller than 2 to the power n time, well, the probability that xn is smaller than u and t, and for all n in 1 n, xn is okay, yeah, I'm sorry. I want this. Okay. I want this. This is what I want. I want to prove that something is small. Okay, so this is the kind of thing I want to go to. I want an upper bound on x max, xn max. So. Okay, and this is just a random walk with Gaussian increments. Okay, because for each v, okay, this thing is a random walk with Gaussian increments. So here I just want the probability that the endpoint is above a certain threshold, and at any time before, we are below square root of 2 log 2 n plus log n. Okay. So let's try to evaluate this probability, and then we will kind of tune this thing, okay, in such a way that this thing goes to 0. I mean, this thing goes to 0 faster than 2 to the minus n. Okay, so like the right threshold will be when this will be exactly of order 2 to the minus n. So we are playing the same game as before, except that now, okay, we have an additional constraint. Okay? Okay, so what's... So, any questions so far on what we are doing? So let me draw the probability. Well, let me draw something, and then we will try to figure out what this means. So here is, I guess, log n. And let me draw here a slope with, so this is log n plus square root of 2 log 2 n. Okay? We have a walk which is starting from here. It has Gaussian increments. And okay, this is un. Okay. Like un might be slightly below, square root of 2 log n. Okay, and yeah, we want our walk to end up in this region. Okay, but we want that before doing so, it never goes above the orange line. So the probability we try to estimate, well, let me write it in a different fashion. So it's the integral from what? Yeah, from un. Okay, up to, well, if you want, up to infinity, but I can stop the integral at this level, okay? Then I have 1 over square root of 2 pi, but I don't really care about it. I have what was the important thing is that I have n here, okay? 1 over square root of 2 pi n. Here I have exponential minus s squared over 2n. Okay, and here I have ds. And then I have to, okay, ds is here. And before I integrate, I have to multiply by the probability that for all n in 1n, xn is smaller than square root of 2 log 2 n plus log n knowing that xn is equal to s ts. Okay? What I'm doing here, this is the probability density of this variable. Okay? I'm integrating along the spot I want to land on. And here, yeah, I want to have the probability that the rest happens, okay, conditioned to the position of the endpoint. Okay, and now is the crucial point. Like, okay, before the conditioning, this was something very unlikely. But now, okay, this is the magic of Gaussians, but this would happen, okay, also for if you had other types of increments. Just for Gaussian, the good thing is that the computation is exact. Like, if you look at the distribution of this blue thing, okay, conditioned to the endpoint, well, it doesn't matter. The distribution does not depend really on where the endpoint is. Okay, in the sense that what it is, it's just a bridge between 0 and 0, okay, plus an affine function. Okay? So what we have here is, okay, this thing here. Okay, you want an upper bound on this. So this is the same as, well, the probability. This is smaller than the probability that for all n in 1n. Okay, let's assume, okay, that un is larger. Okay, that un is larger than square root of 2 log 2 n minus, okay, let's put log n square. Okay. Okay, let's assume that this is true. Then basically, the distance between this line and this line, okay, it's always larger than log n square. Okay, than 2 log n square. Okay, so xn is smaller than 2 log n square, knowing that xn is equal to 0. Okay, and yeah, I mean, like we want to get an improvement over the other thing. So if this thing is violated, we get a tremendous improvement. Okay, and now this thing, okay, this is smaller than, okay, basically a constant over n, and here you have to put this level here to the square, I think, log n to the 4th. Okay, so this is not the computation I will do, okay? But basically, okay. Let's look at a random walk which starts from level A, okay? If you want it to avoid 0 for n steps, okay? Basically, well, if it avoids 0, it will reach level square root of n, more or less. Okay, like it will be, yeah, it will be, it won't go much above square root of n, and it won't go much below square root of n because it's larger than Gaussian times square root of n conditioned to be positive. So basically, you can say, okay, it's like if I'm playing the gambler's ruin problem, but between levels 0 and square root of n. So the probability that I reach 0 before I reach square root of n, well, it's just going to be a over square root of n. Okay, now here I don't have a walk, I have a bridge. Okay, and the walk is Gaussian, not +1, -1. It doesn't really matter. But basically, what happened at the two extremities of the bridge are kind of independent. Okay, what really happened is what you do in the very first steps to avoid hitting there. Okay, so for this reason, if you have a Gaussian bridge between A and B, okay, I think the computation is kind of easy to do with Brownian motion using reflection principle, okay, and you can get the exact expression for this. But the asymptotic equivalent, okay, when A and B are much smaller than square root of n, is A over square root of n times B over the square root of n. Okay, and here, A and B are log n square, so what I get is log n to the fourth. Okay, the important thing is that we have exactly the same thing as before now, except that instead of 1 over square root of n, we have 1 over n to the 3/2. Okay, so what we get out of that computation, and I think you will be happy if I stop writing detailed computations at this point. What you get out of all this, okay, is that, okay, so let me write this as a theorem, is that x and max smaller than square root of 2 log 2. Okay, larger. Minus, okay, and now let me put this in red. Okay, 3/2. Yeah, just the 3/2, because 3 is not 1. This is an important bit. Okay, log n. And say plus c times log n goes to 0 and goes to infinity. Okay, this log n is just to absorb. Yes, this is not there, right? This is there. These A and B, they come at the top. And things, yeah. Right. Things get easy, I mean, like the probability gets bigger when this is bigger. Right? Okay, so you just need some log terms, okay, just to eat that term there. Okay, so what I claim is that basically we just, okay, up to some details, this was a proof of this statement. Okay, so, okay, perhaps this is just a proposition, but no. I'm going to upgrade it into a theorem. So what's actually the theorem is that, well, this is actually, okay, this is not sharp. Okay, you see that when I gave you, well, first, it cannot be sharp. I'm not telling you what the constant is. But you see that you don't really need this log n here, okay? And somehow, there should be a way you can refine this, okay? Basically, you just need to lower this thing here. And okay, it's difficult to lower it in the first part, but perhaps in the second part, you can lower and make it kind of close to un, okay? So, so yes, this is sharp, okay, in the sense that you can prove that this distribution is tight. Okay, so that it converges along subsequences. Okay, and in fact, you can even prove more. What has been proved is that this thing, okay, converges. So basically, what we are doing here, when we restrict to that event, okay, is sufficient to take care about the correlations between the XVs. Okay, so yeah, not only you're able to say that these correlated variables, they behave different as the IID variables, but you're being able to say exactly what's the difference. And the difference is, is basically you get 3/2 instead of 1/2. And the reason is that, n to the 1/2 is the probability that you, for a random walk to end up at the specific point. And n to the 3/2 is the probability that a random walk end up at a specific point and remains positive. Okay, so this is the reason why you get 1/2. But what's more is that you can identify the limit. So the probability that this is smaller than t, it converges when n goes to infinity to something. Okay, so what's better is to say that this converges in distribution to z. Okay, and okay, so this is a theorem by Elia et Decombe, and yeah, I don't know exactly when it. Yeah, let's say something like 13. The 11. The paper was in the archive much before. Well, the interesting thing here is that, okay, you can identify what Z is. And Z is not a Gumbel random variable. Okay, so what is Z? Well, Z is, well, it's really Z1 plus Z2, where Z1 and Z2 are independent. Okay, so Z1 is a Gumbel random variable. Okay, what's Z2? Okay, so yes. If you remember, okay, what we have, so far this proof had very little relation to the partition function of the polymer model. It was just in the proof of the lemma, okay? But it turned out that this thing here is very important. So if you take this thing, okay, it's not difficult to show that this thing goes to 0 as n goes to infinity. Okay, and the reason is, well, if you look at this thing, okay, it's essentially supported by trajectories that end up right there at this level. Okay, at level square root of 2. Okay, because you know the expectation of Wn beta c is equal to 1, and when you look at the expectation here, well, you get the square root of 2 log 2 xn minus 2. Yeah, minus n log 2. Okay, this is you get, okay, the sum over v, but, and you see that, well, if you constrain the trajectory, if you limit yourself to the trajectories that stay below the threshold at all time, you will see that, well, you will get an expectation that goes to 0. Okay, if you put here indicator xn smaller than square root of 2 log 2 and okay, plus something big, okay, then this thing will go to 0. Okay, so this thing goes to 0, but this thing here converges to some limit. Okay, and W prime infinity is, well, it's positive or notional. Okay, and the reason why it's called W prime, well, it's simply because W prime infinity, it's the limit when n goes to infinity of d beta wn beta for beta equal beta c. Okay, so it's the limit of the derivative of the partition function at critical t. Okay, and yes, z2 is just log W prime infinity. Okay, so yeah, you have this. Okay, you can do a little bit more than this. Okay, somehow, like if you want. Okay, okay, these two things are independent, and somehow, okay, there are basically two contributions. Okay, to this limit, and basically, if you look at the first few steps, okay, you will get the information about z2. Right? Z2 is well, the log of this limit. So if you know this for some n large, okay, but much smaller than this big n, then you know something about Z2. So basically, yeah, this is a randomness that is somehow encoded in the first few steps, and this is a randomness that is encoded in the last steps, and things behave independently. Okay, so yes, okay, so I think this was an illustration about yeah, how a question that might seem unrelated in the first place might come to have a relation. Like if you want really to understand this, well, somehow you need to understand quite deeply the phase transition of the directed polymer on the tree, because you need to understand exactly what happens at the critical point. Okay, and yeah, this result is much more general. It's basically true for not for all omegas, okay, but for most omegas. So basically, you know, if your omegas they are plus and minus 1, somehow you cannot get like you have no rescaling here, so you cannot get a continuous. Like the support of the limit here should be some shift of z, okay, if originally you want z. So basically you need some assumption that the distribution of omega is non-lattice. And apart from that, this is as general as things get. Okay, so if you have another branching random walk, basically the only thing that will change is the value of square root of 2 log 2. But the 3/2 will remain, and yeah, the rest will remain the same. Okay, so we have 20 minutes before the defense starts. So, well, thank you for attending this class. This was a great pleasure to teach it, and I'm available for all questions.